Okay, thank you very much for inviting me to speak here. I was looking forward to being able to spend at least a little bit of time in Bonn, but unfortunately, of course, coronavirus has been a bit of an issue for everyone. And I'm going to talk about zero density estimates of the Riemann zeta function, but I sort of chose this topic partly because it's work that's still in progress that I wanted to share with people, but partly also because I had a hope that this might appeal to some of the harmonic analysts who might be in the audience. So it's definitely a number theory topic, but lots of the questions to do with zero density estimates have a flavor that maybe has taken out some of the number theory issues, and lots of the issues that remain have a more harmonic analysis flavor. And certainly an example of this will be in the sorts of things that I've talked about today. Also, before I get into any of the details, I should mention that everything that I'm going to talk about today is joint work with Kyle Pratt, who's a postdoc here at Oxford with me. So this is all joint work, and it's all joint work that's in progress. So hopefully everything that I say is correct, but we haven't really written this up yet. But let's take a step back. And as I'm sure everyone's aware, the Riemann hypothesis is the conjecture that all the non-trivial zeros, at least, of the zeta function have real part equal to 1/2. And maybe for someone like me who tends to work mainly on prime numbers and care about primes, the reason that I really care about the Riemann hypothesis is because it has lots of nice applications to the distribution of primes. So just for some kind of concrete applications of the Riemann hypothesis, for primes in short intervals, there's the result of Howard-Kramer, which says that if you have the Riemann hypothesis, then you get an asymptotic formula for primes in short intervals, where the length of the interval is about square root the size of the primes that you're looking at. And you get a full asymptotic formula for intervals of length about square root of x between within x and 2x. And similarly, there's a result of Selberg, which says, if instead of caring about absolutely every single possible short interval, you just care about almost all short intervals in the sense of Lebesgue measure, then almost all short intervals of length a little bit larger than log of x squared have the expected asymptotic for the number of primes. And so even these really short intervals, almost all of them get the right number of primes. And so something like Selberg's result seems to be far away from what we're able to prove unconditionally at the moment. But these are nice consequences for the distribution of primes if you assume the Riemann hypothesis. But the unfortunate problem with all of this is that the Riemann hypothesis itself seems difficult to prove. And so these results both remain as conditional results. However, if you analyze the proof of some of these results, actually for lots of arithmetic applications, you don't need something quite as strong as the Riemann hypothesis itself. So the Riemann hypothesis says that absolutely every zero has real part equal to 1/2. But for lots of these slightly statistical questions about primes, they wouldn't be destroyed if there were one or two exceptions to the Riemann hypothesis where the real part was larger than 1/2, provided these exceptions were suitably rare in some sort of statistical sense. So for lots of arithmetic applications, you get almost as good results if you can show that most zeros are close to the line with real part equal to 1/2, rather than necessarily showing that all of them are. Now, of course, we believe that all of them should be anyway, but this means that you can try and prove unconditionally weaker results that are sort of consistent with the Riemann hypothesis. And maybe the classic notation for counting these zeros and for stating these things is n of sigma t, which is just going to count the number of zeros in a box where I'm looking at the real part of the zeros being at least sigma and the imaginary part of the zero lying between 0 and capital T. So I'm just drawing some box here. I know that all the zeros have real part at most 1. So I just, n of sigma t is counting the number of zeros in this box where the imaginary part is between 0 and t and the real part is between sigma and 1. And so this essentially makes sense for some value of sigma between 1/2 and 1 because of the symmetry in about the line 1/2, which follows from the functional equation. And we only need to consider things with positive imaginary part because there's also a reflectional symmetry in the real axis. So the number of zeros of with imaginary part between minus t and 0 is the same as the number of zeros with imaginary part between 0 and t. So n of sigma t is this counting function for the number of zeros in some box. And of course, if you believe the Riemann hypothesis, n of sigma t should just be 0 as soon as sigma is bigger than 1/2. But the point of this is that provided n of sigma t is suitably small in terms of sigma and t, then often we can get the same sort of arithmetic applications as we could get even if we assume the Riemann hypothesis. But showing that this number, which we should believe to be 0, is not too large, we maybe hope is a much easier thing to do unconditionally than proving the Riemann hypothesis itself. So, for example, if we keep on focusing on the application of primes in short intervals, if you had a bound n of sigma t is bounded above by maybe some constant times t to the power a times 1 minus sigma, maybe with a little plus epsilon or something, where I'm thinking of a as being some fixed constant. So if I had a bound of n of sigma t is bounded above by some constant time, and then it's t to the power 10 minus 10 sigma, then I would get an asymptotic formula for the number of primes in short intervals, where the length of the short interval is, in the case a is 10, x than 9/10, and for a general constant a, I would get a short interval of length x to the power 1 minus 1 over a. So this is a way of saying that if n of sigma t is suitably small in this sense for all choices of sigma and t, sigma between 1/2 and 1 and t being a positive number, for the same fixed number a, then I get this asymptotic for primes in short intervals. And the sketch proof of this is somewhat, it's not too difficult, and it's going to be somewhat illustrative for some of the things I want to say later on. So we want to count the number of primes between x and x plus y. So that's what I have on the left-hand side here. And I can use the explicit formula to approximate this by a sum over the poles and zeros of the Riemann zeta function. And the expression's a little bit more complicated than what I've written here, but fundamentally, I get a main term of y because I'm counting primes with the von Mangold function, and then I get an error term, and the zeros that really influence this error term are the zeros with imaginary part going up to x divided by y. So I'm thinking of x as being very large here, and y as being something like x to the 9/10. But it's going to be a function of x and y, and I get this error term, which I'm expecting to be small. And if I want to get the results that I put on the previous slide, assuming the Riemann hypothesis, I know that all of these terms, x to the power rho minus 1, have size x to the half minus 1 in absolute value, so x to the minus a half, and then I can just trivially bound this by the number of zeros. If I don't want to assume the Riemann hypothesis, I can use my bound of n of sigma t, and I can say that zeros with real part sigma contribute x to the sigma minus 1 in that sum. So essentially, the contribution I get is the number of zeros with real part about sigma up to height x over y times x to the sigma minus 1 as the contribution of this inner sum. And so this is just put in absolute values and crudely bounding all the contributions, not trying to get any cancellation between these sums over zeros. And if I then just plug in my bound on the frequency of zeros that have large real part, then this automatically gives me the asymptotic. So this is not some terribly deep result at all. It just relies on the explicit formula and then crudely bounding each term individually by absolute values. And I've maybe swept under the carpet a few like minor technicalities, but this is really what's going on. And we really get results then that are kind of comparable to the Riemann hypothesis if we have very strong bounds on n of sigma t. So it's a result of Huxley, I can't remember the exact date now, but maybe around 1970, who showed that n of sigma t, you can unconditionally get a bound of precisely the form that I put in the previous slide when a is 12 over 5, so 2.4. And so an immediate corollary from what we saw on the previous slide is that if y is of size at least x to the 7/12, then we get an asymptotic formula for the number of primes in short intervals. And despite Huxley's result being basically almost 50 years old now, this is still essentially the best that we can do. So Heath-Brown has improved this by essentially being able to remove the plus epsilon. But beyond that, this is still the world record for how short an interval we can get an asymptotic formula for primes. And this is really an immediate corollary from getting an upper bound for the number of zeros with large real part of this shape. But we believe something stronger than Huxley's result should be true. Of course, we believe that n of sigma t should actually be 0 whenever sigma is 1/2, but the density hypothesis is the claim that you should be able to improve the constant a being 2.4 down to the constant a being equal to 2. This would essentially correspond to some sort of square root cancellation in certain Dirichlet polynomials type heuristic. And so particularly in the 70s and 80s, the density hypothesis felt like a plausible thing that one might be able to prove if you could just improve on Huxley's techniques a little bit, and felt like an unconditional analog of the Riemann hypothesis that was maybe slightly within reach. And the very nice thing about the density hypothesis is that at least if you care about asymptotics for primes in short intervals, you get results which are almost as strong as the Riemann hypothesis itself. So unfortunately, we don't have any terribly good ideas for how to prove the Riemann hypothesis, but we do have various results that are in the direction of the density hypothesis. So for example, Huxley's result is a pretty strong approximation to the density hypothesis. We also know that the density hypothesis holds when sigma is sufficiently close to 1. So there's results of Utila and then more recently improved by Bourgain, showing that this density hypothesis bound holds at least for sigma close enough to 1. And so the density hypothesis has often been viewed as a much more feasible result that you could prove, precisely because it feels much more like a harmonic analysis question, rather than having to deal with some of the more fundamental arithmetic subtleties that are involved in the Riemann hypothesis. And the nice thing about this is that this is weaker but more feasible, but actually for some of the arithmetic applications, it's just as good, or almost just as good. But unfortunately, we've fundamentally been stuck with Huxley's bound for the past 50 years, and we don't really know how to improve our bounds on n of sigma t. So lots of people have worked very hard on this problem, and it's become an important problem in analytic number theory. And I said during the 70s, there was certainly a lot of intensive work on this. And in fact, you can get a improvement to this bound n of sigma t, so you can improve the constant 2.4 to something a little bit smaller than 2.4, apart from in the problematic range when we're looking at zeros with real part very close to 3/4. So if, for example, you could magically tell me as a black box that there were no zeros of the Riemann zeta function in the strip with real parts between 0.74 and 0.76, then we would get an improvement to Huxley's bounds on n of sigma t, and we would correspondingly get an improvement for our asymptotics for primes and short intervals. And sort of similarly along these lines, what we really, to improve on Huxley's result, we really just need to handle the contribution from zeros very close to the 3/4 line. So if for some reason you could come up with some different technique that would show that this sum over zeros had some cancellation in it, then that would be a good enough substitute. And again, you would get an improvement in our results for primes and short intervals. So there's a question in the chat which asks, do there exist zero density estimates for numbers with exactly k prime factors? And the answer is, okay, you have to be a little bit careful about what you mean by zero density estimates, because sometimes the explicit formulae and things look a bit more messy, but essentially numbers with exactly k prime factors for some fixed value of k can all be fitted into a generalized version of this framework, and the results are at least as strong as they are for primes, but sometimes they can be much better. So anything that I say is about primes in this context. There is an analogous version of this statement for products of exactly 2 prime factors, and so there is something analogous to Huxley's results, which then gives a asymptotic formula for numbers with exactly 2 prime factors in short intervals of length x to the 7/12. In some cases, you can do better than primes, but you can always do at least as well as primes. It doesn't make quite so much sense to talk exactly in terms of zeros. Instead, it makes sense to transfer the problem a little bit more into talking about large values of Dirichlet polynomials, which is a very closely connected thing. But yes, essentially, anything that happens for primes, you get analogous results for numbers with exactly k prime factors for any fixed value of k. And sometimes, particularly if k is larger, you can get rather stronger results. I hope that answers the question.
Can I ask you a question also, James?
Okay, I maybe missed your question, Shantara. Could you just call it out?
Yeah, I'm just gonna ask directly. So it says if the zeros were distributed randomly on the 3/4 line, but we don't really expect any zeros to be on the 3/4 line, right?
Right.
So what exactly do you mean?
Okay, so if there are few zeros on the 3/4 line, in the sense that up to height t, there's fewer than t to the power 12/5 times 1/4 of them, then we're good.
Right.
So the only bad scenario that we would need to consider would be if there are about t to the 3/5 zeros on the 3/4 line up to height t. But if they were equidistributed in some way, if they had a fairly regular distribution, then you might still expect there to be lots of cancellation in this sum. So one way that you could try and improve on Huxley's results, which I don't know how to do at all, would be to say, I can trivially improve on Huxley's result unless there are unless there are t to the 3/5 zeros up to height t, and if there are t to the 3/5 zeros up to height t, then maybe they have to have a certain amount of structure to them, and if they do have this structure, then I still get cancellation in these sums. So that's very much the sort of philosophy that I want to think about in this talk today.
Perfect. Yeah, thank you.
So one, maybe I'm about to say this actually. But one way that you would certainly not get any cancellation would be if there was some bad value of x such that x to the power I times the imaginary parts of these zeros on the 3/4 line all pointed in the same direction. So it's certainly not the case that regardless of how they're distributed on the 3/4 line, there would always be cancellation. You would certainly need to rule out certain conspiracies amongst the imaginary parts of the zeros. And this is a question that's then sensitive to the precise values of the imaginary parts of the zeros. And so in particular, if you want to make progress on Huxley's problem, one thing that you would need to rule out is the possibility that there are t to the 3/5 zeros all lying on the 3/4 line in some sort of arithmetic progression. Or most of the zeros on the 3/4 line up to height t look as if the imaginary parts are in some arithmetic progression. So this is one potential bad scenario which none of our results at the moment seem to be able to say anything about. And this idea of there being problems if the imaginary parts have some conspiracy to them is something that's sort of been seen in various different problems, particularly if there's say, an arithmetic progression of them. This would completely change results about Chebyshev's bias, for example, about the distribution of primes in arithmetic progressions 1 mod 4 versus 3 mod 4. So the whole point of this slide is that actually we know a bit more than just Huxley's bound on n of sigma t, which means we can really focus our attention on the 3/4 line. And one dream for how you might try and improve on all of these results is to try and have some bizarre world where either there are a few zeros on the 3/4 line, in which case you're good for trivial reasons, or if there's lots of zeros on the 3/4 line, maybe you can understand some structure about the zeros. And maybe this would be enough to rule out problems like there being long arithmetic progressions of zeros, which would nonetheless enable you to improve on Huxley's results. And we do have results of precisely this flavor when we think about some potential Siegel zeros very close to s equals 1 of Dirichlet functions. We have various arguments that say if you don't have any zeros very close to 1, then you're happy for completely trivial reasons. But if you do have a putative zero very close to 1, then on the one hand, this causes complications, but on the other hand, this actually gives you a lot more structure in some of your sums, which means that sometimes you can prove the result that you are interested in, regardless of whether there is a zero or not, but you split the argument up into both cases. And so implicitly, I'm sort of thinking about doing a dream scenario like that, where instead of splitting up based on the existence of a zero very close to 1, I'm splitting it up based on the existence of many zeros on the 3/4 line. And I'm thinking about, are there possible ways that I could rule out these long arithmetic progressions of zeros? So this was my kind of initial motivation when I started thinking about this problem. What are really the limitations of our results? It turns out it's all to do with zeros on the 3/4 line, and can we rule out some of these sort of reasonably well-known potential barriers of there being long arithmetic progressions of zeros on the 3/4 line? So in my work with Kyle, we've tried to and partially succeeded in developing a new way of trying to think about detecting zeros of the Riemann zeta function, which is sensitive to this vertical distribution of zeros. And so is explicitly trying to rule out these potential bad situations of arithmetic progressions of zeros on the three-quarter line. And this is, and what we have at least succeeded in doing is developing a new zero detecting mechanism for zeros that satisfy certain properties in terms of the vertical distribution, which we're calling half isolated zeros. So I'll say a little bit more about this later, but this is sort of partially inspired by some old work of Heath-Brown, and there's a paper by Mani and Ramachandra who thought about isolated zeros. Before I get into the sort of slightly messier details of what I mean by these half isolated zeros and the sort of connections that this forms to harmonic analysis, I thought I'd state some consequences of this sort of way of thinking about zeros. So one slightly bizarre theorem is assume that the zeros of the Riemann zeta function just lie on finitely many vertical lines. If this hypothesis is true, then we get an improved bound for n of sigma t. So we can improve this long-standing bound of 12 over 5 to 24 over 11. And because we can improve this 12 over 5, then we automatically, for free, get a improved range for when we get an asymptotic formula for primes and short intervals. So we can get shorter intervals under the assumption that the zeros of the Riemann zeta function lie on finitely many vertical lines. So since we had 12 over 20, 24 over 11 in our theorem, we automatically get this for 13 over 24. If you really care about how short an interval you can do, you can work a little bit harder and get a number which is a little bit smaller than 13 over 24. But this is what we hope a sort of proof of principle of this kind of new way of thinking about things. And the key thing that I'd like to emphasize is that, in my mind at least, there was this barrier of how on earth would you rule out this possibility that just on the three-quarter line, there were t to the 3/5 zeros up to height t, potentially in an arithmetic progression. And at least if those zeros are therefore isolated in terms of their real parts, this is a way of getting around that potential obstruction. Okay, so there's a question in the chat for Trevor, from Trevor. I guess I would also say that I'm totally happy for anyone to just shout out and interrupt me at any time. So I will be paying attention to the chat, but also feel free to shout out and interrupt me at any time if there's anything that I'm saying. So Trevor's asking, what sort of uniformity do you need in terms of finitely many, and could I allow finite to increase slowly with t? And the answer is yes, we certainly, in some sense, have a reasonable amount of uniformity. Essentially, you just want some local separation in the real parts of zeros of size maybe log t squared divided by log t. So I'll maybe go into a little bit more details on this later, but provided, but you can certainly weaken finitely many vertical lines in lots of quantitative ways and in actually quite strong ways. So you could have, I mean, somehow if two zeros differ in their real part by sort of a bit less than 1 over log t, then it's almost as if they have the same real part, and they only need to satisfy some sort of rigidity that either their differences are sort of a bit smaller than 1 over log t, or their differences are in the real parts are a bit bigger than 1 over log t for our theorem to hold. So you could have almost log t different vertical lines up to height t. But the condition would be a little bit weirder, but it just needs some sort of horizontal rigidity, at least locally. So maybe it's a good point to pause here and to check that everyone's happy, at least with what I'm claiming and why I at least think that looking at the zeros lying on finitely many vertical lines is not a completely bizarre thing to look at. Okay, seeing no further questions, I think I'll move on a little bit, and I'd like to first of all mention what I mean by half isolated zeros, and to say a little bit more, that I guess I should mention that our hope here is very much that this might eventually lead to an unconditional approach for getting improved results about primes in short intervals. And so, although at the moment we're completely limited to zeros lying on finitely many vertical lines, the dream is very much not to prove things under assumptions on the distribution of zeros of the zeta function, but to get some kind of concrete improvements. But at the moment, we feel like we certainly need a fairly big idea to get to that sort of stage. So here's my definition of half isolated zero. If you're a harmonic analyst waiting for the harmonic analysis to crop up, it will come very soon. So just hold on for a little bit, even if your eyes maybe gloss over very slightly at this stage. But I'm saying a zero is half isolated if there's a certain amount of rigidity in the spacing of other zeros nearby. And so maybe the thing that I would first of all kind of encourage you to look at is the picture that I have here, and essentially blue, at least it comes up as a sort of bluey purple on my screen. It maybe looks slightly different to you. Blue is where you're allowed to have zeros of the zeta function, and white is where I'm assuming that there's no zeros. So I want to say that if there's a zero is half isolated, if every other nearby zero is either reasonably far to the left of that zero, or it lies vertically above the zero. So in my mind, an isolated zero is a zero that has no zeros terribly nearby, or maybe all the zeros are to the left. But the key point here is that I'm allowing zeros to lie above this half isolated zero. So maybe the important part of our contribution is that we're allowing this channel of zeros with similar real parts to lie above this half isolated zero in terms of their imaginary parts. So if we did have an arithmetic progression of zeros, this would essentially be, with a fairly small common difference, this would be a zero at the bottom of the arithmetic progression. But none of the other zeros in the arithmetic progression would count as being half isolated. And so they're half isolated because there's no zeros below them, but we do allow zeros above them. So that's my definition of half isolated zeros. It's maybe a little bit technical to state, but the key point is that we're saying there's locally zeros maybe can lie above, but not below in terms of their imaginary parts. And the Heath-Brown unpublished work and Ramachandra Balasubramanian results, a sort of paper that worked on this, essentially showed that if you didn't have zeros either above or below, so all nearby zeros lied to the left, then the number of such isolated zeros, so they called it isolated, satisfies a zero density hypothesis type bound. So there are a few totally isolated zeros where there's no zeros either above or below. They all have to lie to the left. And we want to get improved results for these half isolated zeros where we're now allowing zeros to lie above. And the key point of this is that half isolated zeros interact kind of nicely with this sort of configuration of zeros that I was concerned about when they lie on arithmetic progressions. So maybe our main theorem is that if you have a half isolated zero in the sense of the slide beforehand, then there exists a short zero detecting polynomial for this half isolated zero. And by this, I mean, there's a, if I'm having a half isolated zero up at height t, then there's a Dirichlet polynomial of length t to the epsilon, which takes a large value at this half isolated zero. So the traditional ways of proving these zero density bounds, like in Huxley's results, is to show that there exists a Dirichlet polynomial which takes a large value at any zero of the Riemann zeta function, and then you can say that the zeros must be infrequent because large values of Dirichlet polynomials are infrequent. But the key limitation in our technique is that we can't ensure that there are short zero detecting Dirichlet polynomials. In particular, for the critical case of zeros on the 3/4 line, it's Dirichlet polynomials of length t to the 2/5 that we are limited to. So these are the worst case zeros, are ones that are detected in the sense that there's a Dirichlet polynomial of length t to the 2/5 that takes a large value at essentially every real zero of the Riemann zeta function on the 3/4 line, but we're not very good at showing that Dirichlet polynomials of length t to the 2/5 rarely take large values. And that's the key limitation in improving on Huxley's results. But for these special half isolated zeros, where we have some assumption on the local vertical distribution, we can prove that there are these short zero detectors. And this allows us to prove very strong results about the fact that half isolated zeros are somewhat infrequent. So in particular, this concept of half isolated zero interacts very nicely with the assumption of the zeros lying on finitely many vertical lines, because if the zeros lie on finitely many vertical lines, then all the zeros of the Riemann zeta function must appear in kind of clumps or clusters, all on one of these finitely many vertical lines, and the bottom zero of any one of these clusters will always be a half isolated zero. So maybe this is a proof of concept as to how zeros lying on finitely many vertical lines is a useful assumption to interact with saying that we got a good control on the number of half isolated zeros, because that controls the number of clusters, and by utilizing these short zero detectors a little bit more, we may be able to also bound the number of zeros in a cluster. And that is ultimately how we get our improvement in the zero detecting and the zero density results.
So does this Dirichlet polynomial will depend on this half isolated zero?
Okay, sorry, yeah, that's a very good question, and maybe I didn't make it clear enough. No, it doesn't. So maybe I'm lying very slightly, but essentially there's one Dirichlet polynomial that depends only on capital T. So it has some fixed coefficients, an of size 1, but depending only on capital T. And this takes a large value for every single half isolated zero with imaginary part between t and 2t. That's how you should think about this.
Okay, thank you. By the way, these an are non-negative coefficients, or they can also negative or positive?
Okay, at this stage, just imagine that the AN are complex numbers bounded in absolute value by 1. So yeah, in particular, if you gave me one complex number, then it's very easy to construct a Dirichlet polynomial that takes a large value at that individual number. It's absolutely vital that this is one fixed short Dirichlet polynomial that works for all half-isolated zeros simultaneously. Okay, Kevin asks, what role is epsilon playing and what does it depend on? So epsilon is just supposed to be some constant that can be taken arbitrarily small. I guess with this setup, maybe I could take epsilon to be maybe 1 over triple log t or something. If you made epsilon too small in terms of t, then suddenly these large values wouldn't be as large as log t to some fixed negative power. Yeah, I guess I'm really trying to sweep under the rug all sorts of dependencies on epsilon. So probably all implied constants everywhere depend on epsilon, and I'm just thinking of epsilon as really being a fixed number at this stage. But there is actually some flexibility and uniformity in epsilon. So this isn't a critical barrier, it's just a technical thing for how I'm presenting everything today. And I guess if we go back to our claimed zero density bound, that epsilon is very relevant for this little o1 error term here. And so in principle, you could make everything quantitative, and you could make this little o1 quantitative. And if you want to make the little o1 quantitative, then it's very important to make this epsilon quantitative. And you want to take epsilon as small as possible to make that little o1 essentially as small as possible, but without destroying the overall conclusion about large values. But I'm certainly going to sweep under the rug all of those sorts of quantitative issues. So we should really think of epsilon as being some very small fixed number whenever we see it, and maybe all implied constants everywhere depend on it. So as I mentioned, this quite quickly gives lots of nice results when you combine it with the idea of zeros lying on finitely many lines, and particularly if you had all of these zeros then being in relatively short clusters, you'd suddenly get much stronger results. So if you imagine all the zeros of the Riemann zeta function occur on finitely many vertical lines, which means that they have to then occur in clusters above half-isolated zeros. And if you imagine that all of these clusters are then very short, then this would actually immediately imply the density hypothesis itself, that we get essentially optimal bounds from the point of view of square root cancellation in large values of Dirichlet polynomials, so that n of sigma t is bounded by t to the power 2 minus 2 sigma. And we'd also get a sharp bound for the fifth moment of the Riemann zeta function as another application of the sorts of things these would imply. So I guess that's a pretty strong assumption that not only are the zeros occurring on finitely many vertical lines, but they all occur in relatively short clusters. But it's a proof of principle as to how these sorts of ideas, if you have a strong control on the vertical distribution of the zeros, then you start getting a strong control on the horizontal distribution. And this has applications for other questions to do with the zeta function that are otherwise completely open. So that's just a sort of proof of principle slide of where these things maybe could lead if you had combined them with very strong other bounds. But let me first of all talk about isolated zeros. So I mentioned there was this unpublished work of Heath-Brown, and I wanted to demonstrate how that worked because that's maybe the starting point for thinking about these half-isolated zeros. So essentially, before I was counting primes in a short interval, by looking at some sum of the von Mansgelt function. This time I'm going to look at some Dirichlet polynomial. So I'll have smooth coefficients, but let's not worry about this. So think of this as just the sum of primes between n and 2n with a weight 1 over n to some complex number rho 0. And I can understand this using Mellin inversion and shifting contours, or essentially the explicit formula. And provided rho 0 is some complex number of reasonably high height, I can understand this short Dirichlet polynomial on the left in terms of the contribution of any zeros of the Riemann zeta function, which are very close to rho 0. So if you're familiar with these things, then presumably these steps will be very familiar to you. If you're not familiar with these things, then I wouldn't pay too much attention. It's just that on the left, we're thinking of having a short Dirichlet polynomial, and on the right, we're understanding this in terms of zeros of the Riemann zeta function. So if rho 0 itself was a zero of the Riemann zeta function, so we were evaluating the short Dirichlet polynomial at the point rho 0, then rho 0 will appear in this sum over zeros close to the number rho 0, and will contribute 1 to the right-hand side. And that means that if there were no other zeros at all in this sum, then the right-hand side would be basically equal to 1. And so this would be saying that the short Dirichlet polynomial on the left-hand side would be taking a value of size 1 at any 0 rho 0 where there's no other nearby zeros at all. Now, it's maybe not totally realistic to expect there to be no zeros at all, but the size of the contribution from each of these terms is essentially dictated by this, this factor n to the rho minus rho 0, where n is the length of this Dirichlet polynomial. And this means that if the real parts of all the zeros that are nearby to rho 0 are all quite a bit smaller than rho 0, then they actually also contribute negatively to the right-hand side. And so the conclusion of this is that I have a Dirichlet polynomial on the left-hand side, and if I evaluate it at a 0 where all other nearby zeros lie to the left, then this Dirichlet polynomial takes a large value at that 0. And so I have some fixed short Dirichlet polynomial which takes a large value whenever I evaluate it at a isolated 0, is the conclusion of this. And then I can understand the statistical distribution of isolated zeros by understanding the statistical distribution of short Dirichlet polynomials, which is then reasonably well understood. So this is a very short and kind of cute argument, I think, and it works in a rather different way to the normal ways of trying to detect zeros of the Riemann zeta function. And this was behind sort of the unpublished observation of Heath-Brown. This was essentially his whole argument, and the paper of Balasubramanian Ramachandra. So we want to do something kind of inspired by this argument, but we want to try and do the same sort of thing if rho 0 is not isolated, but instead is only half isolated, which means that we then need to understand this sum over zeros rho on the right-hand side, and we can't just trivially bound all the terms in the sum. We need to try and get some large value of this sum over zeros. But if we can find a large value of the sum over zeros, then we'd have the same conclusion that we have some fixed short Dirichlet polynomial that takes a large value at this isolated, half isolated 0. And you might hope that there's few terms in this sum, and we actually have quite a lot of flexibility about choosing the precise length of the Dirichlet polynomial. So the length of this Dirichlet polynomial is n, and I've said I want it to be short, so I'm thinking of n as being roughly size t to the epsilon, but t to the epsilon squared would be just as good as t to the epsilon, so I have quite a lot of flexibility in choosing n. And also this is all dictated by my choice of smooth function little w with Mellin transform capital W, and it works essentially for any choice of smooth function. So I could choose whatever smooth function I wanted. So you might hope that I could always choose some value of capital N and some choice of smooth function such that this sum over zeros took a large value. It feels that maybe it would be a really bizarre conspiracy for all the zeros to line up in such a way that for any choice of smooth function and for any choice of short length, we always had almost perfect cancellation in the sum, which would be the only way that this argument would fail to get a short Dirichlet polynomial detecting half isolated zeros. So the question then is, could it be the case that for any choice of short length and any choice of smooth function, the zeros conspire in some way to always make these sums small? And the unfortunate answer is yes, this is possible. That if the zeros close to row zero lie in an arithmetic progression with small common difference, then for any choice of short length and any smooth function w, there's actually very good cancellation amongst these sums. So it's certainly smaller than any power of a logarithm and actually quite a lot smaller than that. And this essentially follows from Poisson summation. So unfortunately, this is our old enemy rearing its ugly head again about the possibility of there being zeros in an arithmetic progression on a vertical line, completely ruining our analytic approach. However, I at least...
Hola Carolina, ¿cómo estás? Mira, es que tengo...
is there a question?
I guess no. Maybe
okay.
people mute themselves.
Yep. Okay. So this is one question that I find completely fascinating. Is there a sort of inverse question to this? So this was maybe what I was thinking about when I was answering Shantaro's question. Could you maybe go in the opposite direction and say, if it is the case for every short length and every smooth function, that this sum is small, does that mean that actually the zeros have to look like somehow being very close to some combination of a small number of different arithmetic progressions with short difference? I have no idea if that's the case, but I don't know of any other kind of concrete local distribution other than looking like approximately some union of arithmetic progressions in a vertical sense that causes an obstruction other than this one about them being a vertical arithmetic progression of zeros. So if anyone has any thoughts about this at all, I would be super interested to hear what you think about it. I think it's very closely related to some sort of well-known difficult problems in harmonic analysis. It's sort of like an L infinity version of the inverse Littlewood conjecture on the L1 norm of exponential sums, which is known to be hard. So I'm expecting any inverse theorem here to be maybe very difficult, but I would be totally fascinated if anyone has any thoughts on that question. But either way, there is an obstruction, and this is somewhat unfortunate because, again, we don't seem to be able to say much about there being these vertical arithmetic progressions of zeros. However, one thing to note is if row zero is half isolated, then although it looks like an arithmetic progression going up, it doesn't look like an arithmetic progression going down, and there's a discontinuity in this arithmetic progression. So this example of there being an arithmetic progression doesn't apply to half isolated zeros. And so you might still potentially be able to get a non-trivial bound for this sum when instead of the zero being in the middle of an arithmetic progression, it's at the bottom of an arithmetic progression. And that's essentially exactly what we do. We do show that for any half isolated zero, we can get a lower bound for this sum over zeros. So this sum over a fairly small number of zeros that are very close by. So you can think of this as being some sort of exponential sum with arbitrary phases, and we want to choose a smooth function w and particularly a length n that scales these phases so that the exponential sum doesn't have a lot of cancellation. And this looks a little bit like a Turan power sum type problem. And indeed, Turan power sums have been used in precisely this sort of form in some of the early zero density estimates that people were working on. However, for this problem, it's very important that we get an exponential improvement over the Turan power sum method. And so we have to develop a new Turan power sum type estimate that gets a polynomial lower bound rather than an exponential lower bound. And that's maybe the key technical contribution that we make in our paper. And this is basically a pure harmonic analysis problem. So if there are harmonic analysts who had fallen asleep in the earlier part of my talk, if you don't enjoy this slide, then feel free to go back to sleep. But maybe this is the one slide where you should give me a chance to see if you find something interesting. So this is a sort of simplified version of our setup for zeros. I want to consider the exponential sum evaluated at a length n, which is just the sum of n to the I theta j summed over r different values of theta j, where theta 1 up to theta r are just arbitrary reals. And what I claim is that uniformly over all possible choices of these real numbers, there is some value of n between in any sort of superdyadic interval where this exponential sum is not too small in the sense that I have a polynomial lower bound in terms of r. And the key point here is that I'm assuming absolutely nothing at all about these phases theta 1 up to theta r. So you can use the Turan power sum method to study this sort of problem, and that would show that there's some integer, maybe there's, say, some power of 2n, where you get a lower bound which is exponential in terms of r. So from the point of view of Turan power sum method, it's absolutely vital for us that we're improving this exponential lower bound, which is maybe the standard thing that you get, to a polynomial lower bound. And this is at the heart of showing that regardless of how the zeros are distributed, provided we have a half isolated zero, we have to be able to choose some length when that sum over zeros attains a large value. So I'd just like to have a few comments about this Turan power sum estimate because it's interesting from a few different points of view. So it's totally vital that I'm allowing real numbers n in some superdyadic interval, because if I just chose all the phases to be in an arithmetic progression, then essentially I would have that this sum has perfect cancellation for a discrete set of points n. And so if I was, so you can set this up so that this whole sum is, say, small on all integer powers of a fixed number, which is often what the Turan power sum method is looking at. So in the Turan power sum method, this lower bound would be completely false in the normal setup where you're restricting n to be some real number raised to some fixed integer to some variant integer exponent. And so it's very important that I'm looking at n being a real number rather than going over a discrete set of points, which is maybe a more normal setup. Another totally vital feature is that in this exponential sum, I have positive coefficients. So I have all these n to the I theta j's with a coefficient 1. Whereas in more normal Turan power sum methods, you maybe have a coefficient cj or something that can is maybe a complex number bounded above by 1 in absolute value. But if you were allowing even just plus or minus 1 coefficients, and so you took away this positivity, then again, this could be genuinely exponentially small for all choices of n in this superdyadic interval. And that's because you could, if r is of size 2 to the power k, you could choose your phases theta j and your coefficients to be plus or minus 1 to make this whole sum look like the kth power of some small difference, which is going to be exponentially small for every choice of n between m and m squared. So it's absolutely vital that we have positivity in the coefficients for this to hold true, as well as us to not be dealing with a discrete set of points, but to be dealing with arbitrary reals. Another slightly odd fact is that it's important that there's somehow some discontinuity in the coefficients, in the sense that the argument that I had before about if the zeros lie in a arithmetic progression, then Poisson summations shows that the sum over zeros is always small, has a corresponding analog in this exponential sum setup, and that corresponds to if I had some smooth coefficients for the weights, so that they were maybe still positive, but they went smoothly up from 0 to 1 and then down to 0 again when I got to the end of the sum. So I had some smooth function f supported on 0, 1. Then again, it can be the case that this sum is just exponentially small for all possible choices of n, and this polynomial lower bound is false. So it's absolutely vital that there's somehow some discreteness in the coefficients that I'm looking at, and they're not smoothly variant up and down. And one further thing is that you can construct explicit examples where this sum genuinely is polynomially small for all choices of n, if you choose particular phases θ1 up to θr. And so a polynomial type lower bound is the best that you possibly can hope for. You can't hope for a lower bound of, say, 1. Okay, so maybe this is the most important thing. So I'll just, the most important technical statement. So maybe I'll just pause here to check that there's no questions about this. There's certain important features of this setup, which we're really exploiting and are completely necessary for this statement to be true. But the key point here is that we're getting this polynomial lower bound.
Do you need m to be sufficiently large with respect to r?
Okay, that is a good question. I think, no, this is completely scale invariant, I guess, because it's completely uniform over all the thetas. So I think it's completely scale invariant, and I could replace all the thetas by something like theta divided by log m, and I would therefore get exactly the same problem for any choice of m. So I think this is completely uniform in m, because it's completely uniform in the thetas. Okay. So I think, so there's then the question in the chat, just m is bigger than 1. I think it's totally uniform in any m which is bigger than 0. Because I think you can just rescale everything on a kind of logarithmic scale by a positive constant to reduce to, oh, I guess you can't have m being equal to 1. Okay, yeah, let's say m is bigger than 1. Yeah, okay. Chat, you're quicker than me. Yeah, let's say m is strictly bigger than 1. Yeah, so it has to be bigger than 0 once you've taken logs, which is when all the rescaling goes on. So that was my confusion. So any m strictly bigger than 1, this holds uniformly for. It's, although I've written it in this format, it really should be done on a logarithmic scale, and then I think it shouldn't matter at all. It's some dyadic interval on a log scale. Is everyone happy with the statement? I apologize for my falsehood about m being equal to 1. Okay, so I just want to very briefly sketch some of the ideas that come into this sort of power sum bound. This function s of n is a can be viewed as a function not just for n being a real number, but for n being a complex number, and moreover, it's analytic for any choice of complex n. So it's therefore natural to, in this case, to complexify the question and to look at this function f of z, which is essentially the same thing with log n replaced by z, but now I'm thinking of z as potentially being a complex number. And I can do a certain rescaling, so without loss of geometry, I can let θ1 be equal to 0 and all the other θj's be bigger than this θ1. Because of this non-negativity and discreteness of the coefficients, I know that f takes a large value when I input a large purely imaginary number. But because f is analytic, I know that its logarithm of the absolute value is subharmonic, and so I get upper bounds for the value of the logarithm at any complex point in terms of the average value on a ball around that complex point, or more generally, I can get an upper bound for the logarithm on any domain in the upper half plane, essentially. And by taking essentially the whole upper half plane, this gives me an upper bound for the absolute value of the logarithm in terms of a bound over the whole of the real line. An integral on the whole boundary for all real values. But I know that this function is trivially bounded on the upper half plane, and I know that it takes a large value at this one imaginary point, which means that it can't be small it can't be super small on any dyadic interval, otherwise the contribution from that part of the integral would contradict this inequality. And I should mention that versions of this whole argument have been also independently proved by other people. So we proved this Turan power sum type estimate in a slightly more complicated form required for zero density estimates. And then we later learned that Will Sarwin, I think, has a blog post on Math Overflow where he comes up with a essentially an identical argument to this. It's actually a bit cleaner than our original argument. And similarly, when I was visiting Princeton several years ago, I talked to Jean Bourgain about this problem, and he also independently gave a fundamentally identical proof of this. So versions of this were independently proven by both Jean Bourgain and Will Sarwin. And I guess I should mention that the example of the fact that you do also have some bad choices of θj where you get a polynomial upper bound, that was also shown to me in conversations with Jean Bourgain. But I don't know, I was kind of pleased when I saw this argument, but I sort of assumed that maybe an argument of this type exists in harmonic analysis for quite a long time. So I would be certainly interested if there's any references on things that do similar stuff to this. It sort of feels like it's the sorts of bounds that are sometimes used in analyzing Hardy spaces, but I don't know the literature very well. So if there's any harmonic analysts that can put me in the right direction for references on this, I would be super interested to hear anything. yeah, I think Will's put a version in the chat where he has his math overflow answer. So how does this work with half isolated zeros? Well, we want to estimate this short sum over zeros, all very close to what this half isolated zero rho zero. And by our construction of half isolated zeros, this means every zero in the sum is either to the left of rho zero or it's above rho zero. And terms to the left trivially contribute negligibly just because their real parts are suitably small, that the individual contributions are just too small. Whereas all the zeros that have very similar real parts to rho zero essentially can be translated back into something that looks like our original exponential Tran power type sum with these different theta j's. I've just noticed that I'm over time, so I hadn't noticed that. So this can then be related to our lower bound for Tran power type sums, which shows that there must be some length of the short zero detector which works. And this gives us our good lower bound for half isolated zeros. So it's then well known that if you have a short detecting Dirichlet polynomial, you get very good upper bounds for the statistical properties of these things. And maybe I'll skip the details of this, but then by working a bit harder by analyzing these clusters, you can rule out, you can say that very long clusters of zeros are also very rare. So this can be done by sort of fairly standard zero density arguments and by adapting arguments which give the 12th power moment of the Riemann zeta function. But combining these bounds shows that there's some critical length of the clusters, which gives the worst case scenario, because we're good if there's very short clusters, because then we trivially have a bound on half isolated zeros. But we can also use the half isolated zero detector in terms of the normal zero detecting technology to show that we also get improved bounds when the clusters are long. And that gives us our new improved zero density estimate. And the worst case scenario now has moved from 3/4 down to 2/3. So again, I'm basically out of time, but the key configuration of zeros that I think is really problematic for this whole setup is if the real parts smoothly increase from 1/2 to sigma, but the imaginary parts look as if they're in an arithmetic progression. And this is the configuration that we really don't know how to rule out. And I view these many bows of zeros as being the key vertical patterns of zeros that one would need to rule out if we want to get improved zero density estimates for the zeta function and improved results for primes in short intervals. So if anyone has any thoughts at all about how you might try and rule out these configurations, I would be super interested to hear. It turns out that I now don't think that the enemy is arithmetic progressions of zeros on vertical lines. I think it's instead these bows of zeros where the real parts smoothly vary, but the imaginary parts look as if they're in an arithmetic progression. And these are the ones that I don't know how to rule out at all. But I feel that if you come up with a good idea for how to rule out these, then we're maybe well on the way to get improved zero density results unconditionally. But yeah, sorry for going over time. I have completely lost track of things. Thanks a lot for listening. I hope this